first thing that we need to do is understand what the hell we're talking about. So what would phi of uv look like in the plane? So you could plug in two different values of t and get the same point. Gamma from a certain interval a to b in the real line to R2 be an injective curve such that we can write it this way, x of t comma y of t. Let u be this region, a to b, well, this should actually be square brackets. This looks like a point. Cross R in R2. So if you don't know what that means, in the plane, our curve is defined like this maybe. And as you can see, it's going to have to only be defined from some minimum x to some maximum x. Hence, it's only going to be defined over the interval a to b. Okay? And so, a to b cross r is just the entire region of R. A to b cross r is just this entire region between the two lines. Because that cross r is essentially saying the y-axis. Okay, here we go. So that's the whole region, U, that we're talking about. Now, we add a third dimension to things. Define phi from U to R3 such that phi of UV is equal to x of U, y of U, v, where x and y are the same functions we saw here. So that this guy is a surface, given the information that the inverse of gamma is continuous. Okay, two things we need to do. First thing, circle. So let's say gamma is a circle. So then gamma of t would be rewritten as sine of t for x of t and cosine of t for y of t. So really, this is kind of a parametric function, but not really, if you get what I'm saying. So, we're going to write this as u. We're going to write this coordinate as v, and this coordinate is phi, right? So then, as we go along the u-axis, actually it might be more helpful to write this as v. As we go along the u-axis, what is going to happen? Well, it's essentially going to trace out the function. So if you don't get what I mean, it's going to do something like this. X of u comma y of u, what is that going to look like? Well, let's start by saying we have sine of x, cosine of x, and y. That's going to look like a helical spiral, kind of. Tracing out the circle over and over. So how do we show that this right here constitutes a surface exactly? Well, two things now. First thing we need to do is show that this is an embedding. Now, that sounds fancy, but what it really means is that it's bijective and continuous. Okay, but we know that gamma is already bijective because gamma inverse exists. And we also know gamma has to be embedding because not only does the inverse exist, it's continuous, which means the gamma has to be continuous, of course. Oh, well, it's also stated to be regular in the problem, you can say. All right. So now we know that gamma is embedding. Phi is just gamma of xy comma z. This is embedding, that makes this embedding. Second thing we need to show is that the differential of phi, the differential matrix, has rank 2. So what that essentially says is that our directional derivatives at each point, not like that. If we have something like this, we're looking at the directional derivative, the partial derivatives here. Essentially, we want to show that the derivatives in each direction are linearly independent. Right? So this is just partial rho partial u, partial rho x, partial rho y partial u, partial rho z partial u. So all we want to do is show that these columns are linearly independent at all times. Okay, so plugging in, we have that this is going to be x prime of u, y prime of u, and rho z is just v, which means taking the derivative with respect to u yields 0 here and 1 here, and these two go to 0 since they're just functions of u. So clearly, these two column vectors are linearly independent. You might ask, what if both of these are 0? Well, then that would imply x of u and y of u are constant. In other words, that would mean we're dealing with a point. But that would mean that phi of t is constant. So you could plug in two different values of t and get the same point. But gamma is injective, which means that can't be possible. So that means these two have to be non-zero. And in every other case, since this is a 0 and this is a 1, the only way these two can be linearly dependent is if this is, 0 times that, which is not possible since these two are non-zero. So we figured out both of the criteria for something to be a true surface is true. And so that means that we're good, and this truly is a surface.